Hello students, welcome to the class once again. I believe you are all doing good and you are practicing questions simultaneously after the class. Till date we have studied about kinematics, we have done projectile motion, we have done constraint motion, and if you have practiced question you would have seen that your understanding and concept will be clear. Now today we will be talking about Newton's laws of motion. Already most of you, and I believe all of you would be knowing about Newton's laws of motion. In class 9th and 10th, you must have studied about Newton's laws of motion, and everyone, the statement of the Newton's law would be very much clear to you all, the first law, the second law, and third law. I'm not going to use this statement right now, just in the beginning of the class, but let me talk to you all about the thing that is force, that is the most common thing which we experience each and every day. Now, what is a force? Force is simply an effect of push or pull. It can be only described as push or pull. You can either push an object or pull an object. The source of application of this force may be different. Again, we can classify force into two types, that is contact force and non-contact force, which I'm going to also mention here, need not to worry about that. So first of all, let us come and understand what is force. Now, if I talk about force, we know that it can be push or pull. So we can classify into push or pull in one way, and we can classify further whether it is a contact force or whether it is a non-contact force. This is the second way of classifying force. We will discuss all upon this: push effect, pull effect, contact force, non-contact force. Now see, I believe that most of you would be playing cricket or football or badminton or carom, anything. In all these games, we actually push an object. In football, we kick an object. So what you do, you're pushing the football in one direction. Now, if I talk about cricket, if you hit the ball with the bat, you're again going to exert a push effect on the ball. Badminton, the racket actually exerts a force on the shuttlecock. Then again, you're exerting a push effect on the shuttle. Let's talk about the carom. The striker actually strikes any coin of the carom and a push effect is created. Now suppose if you are pulling the door, you are actually exerting a pulling effect on the door handle so that the door is opened, or let's say it's closed. If it's open, you can close it again by pulling. So all these are push and pull effect, which you can see. There's several examples which I'm mentioning here. Push effect example: kicking a football will exert a push effect. There are many. Cricket ball can be pushed by, it can experience a push effect by the strike of bat. So striking of bat on ball, that will give us a push effect. Now if I talk about pull effect, you can pull the door handle. Example: pulling a door handle will give you a pull effect. Pulling a door handle so that the door may be opened, that will give you a pull effect. Now, I talked about the contact force and non-contact force. Suppose I have this duster here, and if I exert a force on this duster, that means I have touched the duster, and then this force will be exerted on this duster. Now, similarly, the cricket bat, as it strikes the ball, that means a contact force is exerted on the ball, and then only its velocity may change, its direction may change. Third, if you're pulling the door, again you're exerting a contact force. That means two objects have to be in contact with each other to apply contact force. So this can be classified into object exerts force on other object, exerts force, or actually it's not object, it's actually source exert force on other object by actually touching the object, by actually being in contact with other object. So this is the idea of contact force, being in contact with other object. How can you classify non-contact force? Now non-contact force, sometimes, now see, if you take two magnets and let the magnets you bring close to each other and you're not touching, either the magnets will attract each other or repel each other. That will depend upon the polarity that you have brought close. If you have brought like poles towards each other, then it is so much certain that they are going to repel each other. If you have brought at opposite poles near to each other, then they are going to attract. So such kind of force is non-contact in nature. Similarly, we can talk about forces between electric charge. It's not necessary to bring this electric charge in contact with each other to exert force on each other. Opposite nature charges, if they are brought close to each other, they are going to attract each other. And if like charges are brought near to each other, they are going to repel each other. Again, such kind of force are non-contact. See, here we can see that there is no actually contact required so that a body may exert force on another body. Then again, we will learn further ahead about law of gravitation, and most of you must be having the idea of gravitation. Again, to exert a force, the gravitational force, it is not required the object should touch other object. So such kind of forces are known as non-contact. Here, it is not required for the source to be in contact with the object. It is not required for the source to be in contact with other object, to exert the force. With other object to exert force. Example, gravitational force, magnetic force. Example, we can talk about magnetic force, gravitational force, all this force you all must have experienced once or a while. So this was all about the basics of a force. Now let me tell you, if on an object you are going to exert a force, if one force you are exerting, then certainly its effect can be felt and you will be experiencing the effect of the force. So what I'm going to say, let me show this as an object. If I exert a force on this, then certainly I can experience the effect of this force. Now suppose I exert another force, let me call that force as F2. So again I will experience the effect of force F2 also. And if I apply another force F3, and all the forces are acting simultaneously on the object, so again the effect of F3 will be also felt. So all these forces will have an effect on the net motion of the body, let's say net acceleration of the body, which we'll be talking about more when we discuss about Newton's second law of motion. Now suppose I make a very simple case. This is an object, let's say force F1 is acting here, force F2 is also acting in the same direction, force F3 is also acting in the same direction. Now the effect will be felt, and this time all the forces are acting in the same direction. So we can say that if we eliminate all these three forces with one single force, and let me call that as F. So if I draw an equivalent diagram replacing all the forces with one force F, such that this force is vector sum of all the forces, so the same kind of effect will be experienced whether three forces are acting on the object or whether only one force acts on the object, which is the vector sum of all the three forces. Same is the case as we discussed here. If we vectorially add all the three forces and we eliminate all these three forces by the resultant of when we added all the three vectors, the same effect will be experienced. This is known as principle of superposition of force. So I will write here principle of superposition of force. Principle of superposition of forces. That is, let there may be n number of forces acts on an object. It doesn't matter. It doesn't matter whether the forces are acting along the same line, along different directions, whether they are oriented, but try to keep that all the forces should be acting along the one plane, that is either on the x direction or y direction, in the same plane, xy plane. And if we take the forces acting in a three-dimensional space, it will be quite complicated, but still the net force, the net effect can be felt along the sense of resultant of all the forces. So this is called principle of superposition of forces. That is, you can mention net force is equal to vector sum net force F is equal to vector sum of all the forces acting on the object. There may be n number of forces I'm mentioning in this way. So you can replace all the forces with one force which is the resultant of all the forces. This was all about force. Now what force can do? What force can do? Force can bring certain kind of changes in the motion of body, which I am going to write here. Hope you have noted down here what kind of changes it may bring on an object. So let me write down the effects of force. So effects of force, all you would have experienced. First of all, a force can, the first effect, a force can change the state of body. That is, it can bring a body in rest to in motion, and it can change the state of motion to a state of rest. So what it can do? It can change the state. So the first thing, change in state. So what we can write, change in state? A force can bring a body in motion from rest. Bring a body in motion from a state of rest. Means it will change the state of rest to state of motion, bring a body in motion from a state of rest. So that is what a force can do, and that's very simple. That's very simple. You can see that if I have this duster, as you can see, if I have this duster, then certainly if this is at rest, if I apply a force, then this will be starting moving, this will start moving, and so the force effect is actually nothing. It's what it is doing, it's actually changing its state. It's from a state of rest to a state of motion. Let us talk about the next thing that it can do. It can change the direction of motion. So it can change the direction. Now if I am writing change the direction, what do I mean here? It can change the direction. Suppose a cricket ball, a bowler is bowling and the ball reaches, covering a parabolic path, and it reaches to the batsman. Now if the batsman hits the ball, he can direct the ball to any other direction. That is, he is applying a force. That force is actually changing the direction of ball. So what it can do? It can change the direction of an object. If you kick the football along towards left, towards right, making some angle with the horizontal, anywhere, you are actually changing the direction of the ball by applying a force. So what force can do? It can change the direction of an object. Changes the direction of motion of an object. Changes the direction of motion of an object. Now let's talk more. Let's not stop here. Let's talk more about what force can do. The third thing, most of you would have played with a canvas ball or with a football. Actually, you see here, if you throw a canvas ball on ground, you'll find that it will hit the ground. It will get deformed during the instant, during the moment of time when it is in touch with the ground. Again, due to its property of resilience, it will regain its structure and it will rebound. Similarly, if you kick a football, just at the time of kicking with your leg, the football gets deformed, although in a very small amount, but it deforms and again it regains its structure and then it moves away. So what we can do, it can deform a body, deform an object. A thing that can be noticed, you all can notice this. If you take an object, and you exert force on this, like let's say, let me have this a piece of rubber I'm having, it's a duster here, the duster pad I'm having. If I exert a force on this, I can deform its shape. You can see here, I can easily deform its shape. This is one thing, by applying a force. You can see there are many things of whose shape can be deformed by applying a force. And I told you, for example, if you take the example of a ball. So see here, if a ball strikes ground, its shapes gets deformed while the instant it is in touch with ground. Later on again it gets rebounded and again it regains its original shape. So that's the effect that force can cause by deforming the shape of a ball. This is what the force effect can do. This is all about basics of force, what we have learned. Force can be classified into two, as contact force and non-contact force. Contact force is one in which the two bodies have to be in contact with each other to exert the force. Non-contact force, no contact is required for the force to exert an effect, to make an effect feel. I also told you force can have a push or pull effect. By pushing, if you push an object, you will move the object further ahead. If you pull it, you are pulling it towards. And again, if at your home you would have tried this, you would have pushed a table, you have pulled a table. All these are examples of push and pull effect of a force. Then I told you apply many forces on an object. You can replace all, you need not to apply all these forces. You can replace all these forces by a single force, and this single force should be the vector resultant of all the forces. So we got this, that is called principle of superposition. Now let's come to the first important thing of the class. This is all the short introduction about the chapter about force. Now let us come to the first part, that is Newton's first law of motion, which you are all very well aware of, but I'm going to just give you a quick recap of what do you know, and you can just brush up the idea of Newton's law of motion, and we are going to discuss about first law of motion. Let me give you an idea, although this might be a common and very normal statement for you all. Newton's laws of motion are the fundamental laws. Okay, and this is actually, it works on for macroscopic motion. I mean, it is not applicable where the velocity of objects reaches to a very high value, and the velocity, if it reaches to nearly the velocity of light, and if we talk about very small objects like whose size are nearly the size of atom, their Newton's laws are not applicable. We will see what laws are they are applicable when we read about quantum physics. But in this case, we are going to study about Newton's law that is applicable on finite sets object and which are moving with finite velocities, not with a large velocity that is comparable to the velocity of light. We are not going to deal in such cases right now. So let us talk about Newton's first law of motion. Newton's first law of motion. You all must be knowing that, the statement of this. Before giving you this statement, let me give you some idea about Newton's first law of motion. Suppose an object is kept on table. Let's say this is a duster, it's kept on table. Now I'm not disturbing it. You don't disturb it. It will stay in its state of rest until and unless I'm going to exert a force. If I exert a force, it will move further ahead. If I pull it, it will move backward. Its state of rest will be continued by the object until and unless external force is applied on it. Now, if I make this object to move, it will continue its state of motion until and unless an external force is applied to stop the object. What I mean to say, normally you will say that, sir, if we kick an object on ground, if we kick a ball on ground, ball stops after some time. Just now it is not obeying Newton's first law of motion. The first law of motion says that an object will keep its state of motion until and unless an external force acts on it. But here, where is the external force that is acting on the object? If you are making an object move on ground, or let's say you're kicking a football on ground, there is actually friction force acting, and if you throw an object, it will come down because of gravitational pull and this air resistance acting on the object, which actually exerts a force in the opposite direction, and hence a frictional effect is created, and thereby the object finally stops. So there you are exerting a force to stop the object. To clarify this concept, if you take an object and if you're in space, just throw the object in space, it will continue its state of motion along the same straight line along which it was projected if there is no force is acting on the object, and if it is in space, in a gravity-free space, then suddenly it will continue its state of motion along the same straight line along which it was projected. So that is the statement of Newton's first law, that if a force acts on an object, a body continues its state of rest or state of motion until and unless an external force is applied on it. A body continues its state of rest, or state of motion along the same straight line, or state of motion along the same straight line until and unless an external force acts on it, along the same straight line until and unless an external force acts on it. I hope you are getting this. It's a very simple statement, until and unless an external force acts on it. Now I am talking about external force. I will also tell you what do I mean by external force. Actually, there's a difference between internal force and external force, which we will talk about. Don't worry about that. Until and unless an external force acts on it. Now, clear? I hope that this statement clarifies what Newton's first law is willing to say. That is, if an object is kept on ground, it will continue its state of rest until and unless you are going to exert a force on it and thereby making it to move. Second thing, if a ball is rolled down, it will continue moving with the same speed until and unless an external force is applied so that it may stop. So I am also mentioning this surface is frictionless, so its motion will be continued, so its state of motion will be continued and it will never stop. Now I also mentioned it has to continue its motion along the same straight line. You need to take care of this statement. That is, its direction will also not change. So if you want to change the direction, you have to apply a force also. Okay, so Newton's first law, it's also known as law of inertia. So I am mentioning a statement here. It is also known as law of inertia. Now, how can we describe this law of inertia under three headings? Because you can talk about three types of inertia: inertia of rest, inertia of motion, or inertia of direction. So we can classify it under three broad headings: inertia of rest, inertia of motion, and inertia of direction. How to understand it? Let me write and I will tell you. And I believe that in class 9th, if you remember what you have learned, this is just a class 9th thing that I am writing here, inertia of direction. That is, if no force is acting, so body will continue its state of rest. If no force is acting, body will continue its states of motion. Now again, to change the direction also, you require to exert a force. If no force is acting, the body direction will not change. It will be along the same path along which it was made to move. Now inertia means what? Inertia means actually to restrict. So you may just take down an extra statement. Inertia literally means to restrict. So actually you can think of that the bodies are lazy. Bodies are lazy, or let's say body wants that whatever state I am in, let me be in that state. If I am resting, let me rest. If I am moving, let me move, and do not change me. That is what is required for everybody in the entire universe. That is the statement of Newton's law. Now more thing we can talk about Newton's first law. You can think of an example everywhere. If you are resting, you will be at rest. If you are moving, you will be at motion. Now you can also relate why your knees pain when you walk, why your muscles get tired. It's very simple, because the opposite forces are also acting on your body. That's why your knees or your muscles are paining when you walk. And frictional force are also in operation, so that you have to overcome the frictional force and then you are able to walk. So that's why your muscles are working out, so that's why they pain. Now let's talk about, this was a simple statement of Newton's first law, and there will be no numerical application of Newton's first law. You should just have an idea. Let us talk about the most important and most basic law, which is the most applicable nearly everywhere. This law is Newton's second law of motion, and let me tell you, the entire chapter is dependent on Newton's second law of motion. Now one more thing, Newton's second law is not applicable only in this chapter, it will be applicable nearly in every chapter. Call it gravitation, call it electricity and magnetism that we are going to learn, call it electrostatics in modern physics, nearly everywhere we are going to apply Newton's laws of motion. And even to derive such basic relations, in coming chapter we'll be finding that Newton's second law will be of so much of use to us. So let's understand Newton's second law of motion. Before giving you this statement, let us see the effect of force, what force can do. I hope that you are remembering the basic points about acceleration, mass, all this thing. And if you remember, acceleration was given as rate of change of velocity. So let's talk about Newton's second law of motion. Newton's second law. Before writing this statement, let me make you understand. Let us say this is a body and I am going to apply a force on this. Now if I am going to apply a force on this, and this force is of such of magnitude so that it can overcome the frictional force which the ground can exert on this body, so this object will start moving. Now as this object starts moving, that means due to the force effect, it will have some acceleration. Now if it has some acceleration, further what I am going to do, on the same body, I am going to apply a force of magnitude 2F. Let us simplify the case. Let us say this ground, in this case it is frictionless. No friction is acting. Now if I am going to apply a force of twice the magnitude of initial, what we are going to find? We are going to find this time the acceleration of body is twice to what we have found out in the earlier case. If this was A acceleration in the first case, so it will be 2A in this second case. Further, to verify our observation and to come into and to reach to a conclusion, what we are going to do, we are going to apply a force of magnitude 3F, and this time we will observe that acceleration produced is 3A. Let us take a very simple example. What you do, you take a table at your home or take a chair and try to give a push effect on it, and you think that how much force you are applying. You will see that the table or chair will move forward. Now what you do, just increase the force and think that you are increasing the force, and now you are applying twice the magnitude of the force what you have applied earlier. So you will observe that this time the table or chair's acceleration will be twice of the acceleration what you have observed earlier. Further, if you are going to increase the force further ahead, you will be seeing that this force will cause an increased acceleration, and if the force is increased to thrice of its initial value, the acceleration will be 3 times. Let me take a very simple basic day-to-day example. If you are riding a bicycle, what you are going to do, you are going to exert a force on the tires and the tire rolls down and then you are moving. Now as the bicycle tire rolls down, what you are going to do, you are going to paddle it. What you are going to do, you are going to paddle it using a simple mechanism. And if you are exerting a force on the paddle, if you are exerting a force, you will find that this will have some acceleration, let's say A acceleration when you exerted force F, let's say. Now if you increase the force, you will find that the acceleration will be just twice of the case that was earlier. Now acceleration will become twice of the initial acceleration that you are going to observe. So what we are seeing, the effect of force is directly proportional to the acceleration that has been produced, or we can say the acceleration produced is directly proportional to the force which was applied on the object. Here comes this statement, the second law statement. Newton observed this very closely and he reached on some conclusions. He said that the force exerted on an object produces an acceleration, and this force and acceleration are directly related to each other. That is, we can write this force is proportional to acceleration produced, and the proportionality constant he used as the mass of the object. So this simple statement is actually the statement of the second law, that is, the force applied on an object is equal to the product of mass and acceleration produced in the object. So what is statement we may mention here, we may write this statement of the second law as, I am rubbing this statement, I am rubbing this diagram. You may write down the force applied on an object, or to be more precise, the net force, you may write the net force applied on an object is equal to product of mass and acceleration, is equal to product of mass and acceleration. I believe that this concept is clear to you all. In simple words, what we can write? We can write F net is equal to mass into net acceleration of the object, or we can write, if there are several forces acting on the object, we can write sigma F is equal to mass into acceleration. Even this statement is also valid, and even the earlier statement is also valid. F net equals to mass into acceleration net, or sigma F is equal to mass into acceleration. This is all about the basics of second law. And I will also teach you how to apply the second law, what steps we need to use, so that a complicated case can be simplified into a more simple one. Okay, in this Newton's second law also, we have a hidden concept of equilibrium of an object. Now see, if I tell you equilibrium, that means the net force on the object should be 0. So for linear equilibrium, we can write down, because in the second law we can also write one more thing, equilibrium of an object. Equilibrium of an object. We can write down the net force, a body to be in equilibrium, the net force on it should be 0. For a body to be in linear equilibrium, for a body to be in linear equilibrium, for a body to be in linear equilibrium, net force on it should be 0. Net force on it should be 0. Now see what we can do actually. And right now we are talking about linear equilibrium. We are not talking about the rotational equilibrium, and which I will tell you in detail in coming chapter. That for rotational equilibrium, the net torque on the body is 0. I am not using all these vague terms, because that will actually confuse you all. What is torque, what is rotational equilibrium? So I'm not using this. I'm just talking about the linear equilibrium, and that is on a body the net force should be 0. Now see, the force can be resolved along two axes, x axis, y axis, and if all the forces are acting in space, even we can further resolve along the z direction also. So let us take for linear equilibrium, we can write down for linear equilibrium, we have, for linear equilibrium what we have, the forces can act all the three directions. So net force along any of the three axes should be equal to 0. So we can write sigma fx should be equal to 0, sigma fy should be equal to 0, sigma fz is equal to 0. When I write f, that I mean net force along z axis, the net force along y axis, and net force along x axis should be 0. Then the body will be said to be in linear equilibrium. I talked about force equal to mass into acceleration. Now these forces can be of different types, which we'll be seeing in coming session, that I will telling you the normal force, the tangent force, and then how to apply the tangent force, how to find out the normal force, which is not possible in today's class, but I will tell you in the next class also. Don't worry about that. Prior to that, let us discuss some of the basic examples for in the case of Newton's second law of motion. And see, in today's class, don't worry, I am not going to detail of how to apply Newton's second law, and let me tell you, it will be very easy, and it's quite a lengthy steps involved to understand how to the basic methods to apply Newton's second law of motion. The time is not will not permit us to do it today, but certainly in the next lecture I will take care of that. Let's do a very simple case. Suppose on this body you are making, let's say the body of mass is m, you are exerting a force of, let's say, magnitude 20 Newton, an acceleration of, let's say, 2 meter per square second is produced. And see what we are going to do, we are also exerting a frictional force on this, let's say frictional force that this body is exerting, that is equal to 4 Newton. Frictional force that the body is exerting on this moving object. This object is moving, on this moving object, frictional force is equal to 4 Newton. Now, in this case, don't worry. In this case, the friction, just take the frictional force acting opposite to the direction of motion of the object. This will be something like this. Body, apply the force 20 Newton, apply the frictional force in the backward direction, that will be small force F 4 Newton, and the net acceleration that we have written as 2 meter per square second. Suppose it has been asked, find the value of mass of the body. Very simple case, which I know that you will be thinking that what a simple question we are discussing in class, but don't worry, let's start with a simple one and then we will take up complicated cases as in the practice what we do. We have in each chapter we are practicing good questions also. Here the net force on the object. See, net force, F 20 Newton is acting in the forward direction and 4 Newton is acting in the backward direction, and forces I told you are vector quantities, so hence add them vectorially. If you add them, you find that net force in the forward direction will be 16 Newton. So we can write net force is equal to 20 minus 4 is equal to 16 Newton, and just now we wrote that F net is equal to mass into acceleration, hence mass is equal to F net divided by A. That will come out to be F net, that is 16. 16 divided by 2, that comes out to be 8 meter per second square. This is, sorry, 8 kg we need to mark down. I wrote meter per second square, that is the value of acceleration. 8 kg is the value of mass of the object. This is what we are observing and how to apply the Newton's second law. Again, I told you this is just a simple basic example. The forces can act in various directions. The mass can move combined with several masses through strings, through pulleys, on tables, sometimes hanging. So sometimes masses may move on an inclined plane. All these cases we'll see how to apply Newton's law. So we talked about equilibrium. Let us see how we can discuss about equilibrium on an object. Second example, on an object, let us say two forces are acting. One is F1, 3 Newton, and one is F2, 4 Newton. These two forces are acting on the object. Suppose we want that the body should be in equilibrium. Then it is required what one force that you need to exert on this object so that the body remains in equilibrium. So let that force be equal to F. Now that force should be equal to the opposite of resultant of this force. That is equal to negative of the resultant of this force. Now if you see these two forces, the resultant will be somewhere here. And it's very easily you can find out the resultant of these two forces will be equal to 5 Newton. To keep the body in equilibrium, the net force on the body should be 0. What you do, apply a force just in the opposite direction. So this is the F required for the body to be in equilibrium, and F required is 5 Newton. That is. So we talked about equilibrium, we talked about Newton's second law. Today's class, we started with understanding force, its contact force, non-contact force, its push effect, pull effect, and then we learned about what forces can do. It can change the state of motion, state of rest, and it can change the direction. It can deform a body. Now, one more thing. Later on, we started Newton's first law of motion. An object continues the state of rest or state of motion until and unless an external force acts on it. We talked about Newton's second law of motion, and Newton's second law, we saw that F is equal to mass into acceleration. We will use it wisely in the coming class. I will teach you how to use it. And prior to that, I will tell you what kind of forces will come in general. We will see normal force, tangent force, and other kind of forces, how to find them. I want you all just to have a quick recap of this, just revise. This was an easy class, just revise, and I'll meet you in the next class. Till the time, this is Abhinav. Thank you everyone.